Good afternoon. My name is Lisa Matthews, and I'm with EPA's Office of Research and Development. Thank you for joining us for today's EPA's Tools and Resources webinar series. Our webinar today is going to focus on nutrient management in coastal communities, including some promising results from a challenge to design septic systems that can remove nitrogen, as well as our broader nutrients research efforts, which have been focused on Cape Cod and how they might be applicable to other communities with similar challenges. If you have a question during the webinar, we ask that you please type it into the chat pod. And once the presentation is over, we will go through as many of those questions as time allows. I want to point out that the slides from today's presentation will be posted to the EPA research website. Please mute your phone if you are not speaking. The slides from today will be posted to the EPA research website, and you will be able to find them there. Amy will type that address into the chat pod. They should be posted in the next few days. And once the presentation starts, we're going to mute all the lines to cut down on background noise. So at this point, I want to turn it over to Dr. Bill Fisher. Bill is our Associate Director for Ecology in ORD's National Health and Environmental Effects Research Laboratory, and he is going to introduce the topic and our speaker for today.
Thank you very much, Lisa. If anyone can't hear me or can't hear me well enough, please speak up. It is indeed a pleasure today to introduce Dr. Timothy Gleason. Dr. Gleason joined EPA's Office of Research Development in 1995, and I think for at least about 10 years he has served as the branch chief of the Monitoring and Assessment Branch at ORD's Atlantic Ecology Division, a research laboratory in Narragansett, Rhode Island. Among his many contributions to EPA research and research management, Dr. Gleason worked very closely in the early 2000s with EPA Region 1, which is the New England region, to develop the Southeast New England program consisting of several state environmental agencies, the regional partners, universities, and non-government organizations to address environmental issues in the New England area. And he continues to serve on that steering committee, a very successful committee and program which now receives annual funding from EPA. Dr. Gleason received his Bachelor of Science degree. He's a New Englander from Bates College in Lewiston, Maine, a master's in fisheries and aquaculture from University of Rhode Island in Kingston, and his PhD in biological science at URI, University of Rhode Island, as well as an MBA. So he's very well versed in a variety of fields. I should also mention that he's an avid kayaker, and if you're planning any trips by kayak, he's a good person to talk to. Today, Dr. Gleason will update us on three topics that are relevant to nutrient management in coastal communities. First, the septic sensor challenge that Lisa referred to, exploring social ecological systems, and also an update on ORD's Nutrients Translational Science Project, for which Dr. Gleason is the project lead. And Tim, with that, I turn it over to you. And thank you for making this presentation.
Thanks, Bill.
The leader has muted your line. To unmute your line, press #6.
All right, thanks, Bill, for that nice introduction. So today, as Bill mentioned today, I'm going to describe really the work and efforts of a lot of people, a lot of staff. And so I'm just the messenger. I don't want to be taking credit for the work that's been done by everybody here at AED and actually across ORD. I'll be providing snapshots of a lot of different pieces of our research. There won't be adequate time to go into detail on any of them, But certainly if there are pieces that you'd like to follow up on later, we can connect you with the appropriate researchers so that you can dig in more deeply to any of these topics. So I'm certain most folks on the phone are pretty familiar with the impacts of nutrient pollution in coastal systems and water bodies in general. But certainly low dissolved oxygen, algae blooms, things of that nature in the estuarine systems, loss of seagrass, changes in the biotic community are all things that are signs of impairment due to nutrients. The cost of interventions can be very high, and there can be social barriers to various interventions. So we have a suite of research that tries to get at all those different bits and pieces. So we've done a lot of our work on Cape Cod, and Cape Cod's kind of a convenient model system for us. It's nearby, so we can get there in a day, but it represents a problem that persists across the East Coast and much of the United States. On Cape Cod, there are 34 watersheds that have total maximum daily loads, or TMDLs, for nitrogen, and it's driven by non-point sources, largely septic systems. Agriculture is not a big contributor in this system. Sewering, as I'll talk about later, is an expensive problem, and there's already a lot of nitrogen in the groundwater that even if you could magically turn off all the sources today, the problem would persist for decades. As I mentioned, other regions face similar sets of problems. So we're trying to use Cape Cod as sort of our experimental model system for this. So just a quick outline of what I'll talk about today. I'll describe the septic sensor challenge, and then I'll talk about our nitrogen research on Cape Cod that consists of two pieces. The first was done in our most recent research program and is winding up now, is really looking at social ecological systems and how we conduct research to support that. And the second piece being the translational science pilot that I'll talk about at the end. So the septic sensor challenge grew out of our Cincinnati office of ORD and through out of the water cluster initiative. And the goal was to incentivize the private sector to engage in helping solve some of the nitrogen problems. And so one challenge is that evaluating how septic systems perform, particularly new septic systems, is costly. It costs money to physically go out, take the sample, bring the sample in, run it through a laboratory, and the goal was to come up with a sensor that would allow the cost for this to go down so that we could get better data, we could get faster data, and folks would know how their systems were performing, and communities would know how well they're meeting their nitrogen challenges. And so some of the benefits of that sensor development would be, assurance of long-term system functionality, reduced cost of data collection, minimizing human errors. It could create a new market segment for industry, so there could be opportunities there, and homeowners and communities would have assurance that their individual IA systems, innovative septic systems, were working as advertised, and help identify when systems were out of compliance so that could identify when to intervene and take steps to improve or maintain systems. And there were a number of different partners for this work, ranging from the Nature Conservancy to the Massachusetts Alternative Septic System Test Center and multiple parts of EPA and state and regional people. So a lot of interest in this topic, and there's a suite of sensor design specifications identified. Just want to point to the top two, and the goal is to have an installation price of $1,500 or less, and at a minimum to be able to measure nitrate and ammonium. Ideally, additional nitrogen metrics and lower cost, but as a first blush, those two at a cost of $1,500 per sensor. So in phase one, we partnered with the USGS and the Nature Conservancy and had written submissions and identified multiple folks that succeeded. And the first place prize was given to a Yukon team that developed an inexpensive sensor that could be printed using a three-dimensional printer. Really interesting, low-cost sensor technology. The challenge will ultimately be putting that into a hardened system that could be used in the field. And so the winners for this were announced about 2 years ago. We've gone on to a second phase of the challenge. And the second phase involved field testing at the Massachusetts Alternative Septic System Test Center. And we have a 1-week screening test coming up this summer. For companies or for entries that pass that 1-week test, there'll be a 1-month test in December. Then following that, any successful candidates from that could go into a 6-month field trial. And any that pass that 6-month field trial will get ISO certified, and the Nature Conservancy is prepared to order 200 of those sensors. And ultimately, this will all run through Verified Global, and it's a unique piece where we have EPA working with NGOs, working with private entities to identify a tool that can help all of us address this nitrogen challenge. So with that, I'll move on to the nitrogen research on Cape Cod. These are figures from the Cape Cod Commission's 208 report. That report's a few years old now. I suspect the sewering cost estimate has crept upwards closer to $8 billion now. And so that's one of the challenges with solving the problem on the Cape, is that the population is distributed broadly, and the cost of putting in sewers, they have to account for the peak seasonal load that occurs 6 to 8 weeks a year. And so you have to overbuild a lot of capacity, and because the population is distributed so much, there's a lot of pipes and plumbing that has to go in the ground to reach homes. So communities would like to find less expensive and less intrusive ways to solve that non-point nitrogen problem. And the box on the right is just a snapshot of what the Cape Cod Commission has put together, as it referred to as their technologies matrix. And the technologies matrix lists a number of potential green, nature-based solutions to solving the nitrogen problem, with estimates of how much nitrogen can be removed by these and estimates of cost. And so that allows the towns to start to think about what alternative approaches or suites of alternative approaches they might employ. The challenge is a lot of those numbers are fairly coarse, and these systems aren't that well understood, so towns are a bit reluctant to invest lots of money in these solutions when they don't really know if they'll get the performance they need, and they're afraid they'll spend money, they won't get the performance, and then they'll still have to go out and sewer and do other things. So that's an opening for us on a research side to step in and try to address some of these. And the first bit we did was to evaluate how social ecological systems to help with adaptive management might come in. And just real quickly, the idea is that if there's a change in the environment, there's a social impact to that. And that social impact can then lead to policies and interventions which then have an environmental impact again, and that cycle just kind of repeats itself. And so how can we evaluate these pieces, look for where it's smart to intervene, and how to evaluate that performance so that we can continuously adapt these systems and improve over time. Within that research program, there was a suite of research that was conducted. One key element was stakeholder engagement right from the beginning, but there was experimentation. We looked at the impact of seawater intrusion on some of these alternative septic systems. We looked at whether living shorelines could be used as a tool to increase wetlands and possibly remove nitrogen. We evaluated on a social science basis some of the barriers and opportunities to using alternative technologies for nitrogen removal. Looked at how we might do optimization of alternative technologies to evaluate in a dynamic context how mixes of technologies might be used, develop structured decision-making tools, looked a little bit at some of the restoration of wetland systems, and ultimately also explored recreational demand in waters. Recreational demand as it relates to water quality in these systems, or perceived water quality. So I'll talk briefly on each of these and what we found. So the seawater intrusion experiment, some of the novel septic systems being developed now are using wood chips underneath leaching fields as a way to promote denitrification. And those systems have various names. On Cape Cod, they're called the layer cake. In any case, these show a lot of promise for being an inexpensive, low-maintenance way to remove nitrogen. But there's a lot of concern in the coastal system that with sea level rise, that these systems may get more seawater inundation. And so we wanted to conduct an experiment to evaluate that and how well whether that would impact the performance of these. So our scientists worked with a local sewage treatment plant and developed these experimental systems that you see in the picture that had a mixture of sand on top and wood chips on the bottom that mimicked these septic systems, and looked at how various levels of seawater inundation impacted the denitrification process. And in short, they did not materially impact nitrogen removal, which is a very positive sign for these systems that might be in coastal environments. On the living shorelines front, we wanted to look at whether you can reduce salt marsh loss and erosion, potentially also increase denitrification and stabilize shorelines, with the goal to promote healthier salt marsh habitat and also evaluate the use of biodegradable materials. So everything used in this experiment was biodegradable. The big curving logs in that lower right picture are made of coconut fiber. And we found some evidence of nitrogen removal based on denitrifying enzyme activity. We saw that the marsh eroded less behind these systems than it did in other systems, and found that the log restoration, core log restoration, would be more successful if you place oyster castles or other reef balls, hard structures in front that could break up wave energy. Ultimately, we had a couple of big northeasters that did some damage to these systems. So something that could limit the wave energy would allow this system to work better in the northeast. For evaluating barriers and opportunities, we use semi-structured interviews and focus groups. And one of the key findings really is that acceptance of these innovative technologies or new techniques is more involved than just nitrogen reduction, efficiency, and engineering costs. That the public has to accept these. They have to not mind the view or the sound or the interruption that goes with putting these things in place. And so we really need to continue to work with the public to understand the acceptance side of this and not simply look at this from a how many pounds of nitrogen at what cost these can be removed if we ultimately want to be successful. The other piece is that more pilots of these technologies are important so that we build trust, and there'd be more trust if these pilots were conducted locally on Cape Cod for people to believe that these things actually work. So in the dynamic optimization, one of the things we looked at was the trade-off between groundwater travel time, which in some cases is 10, 20, or 30 years, and the use of oysters in the water body itself with changes in septic systems, and how much the of the overall cost could be reduced by adding something like oysters in the water as opposed to sewering or putting in new septic systems everywhere. And we found that with a certain amount of oysters added, we could lower the cost of the more expensive gray technologies. Oysters wouldn't be a replacement, but they could offset some of the more expensive distant homes. And they had the added benefit of being in the water body, processing the algae blooms and the algae that were being caused by nitrogen that was already loaded into the system. So it could save significant money to add aquaculture as a part of the solution. We also conducted some decision science work, with the goal of helping evaluate different types of IA systems and provide an adaptive management plan for determining which IA systems to employ at scale. And along those lines, we also use these approaches for helping to monitor the benefits of ecological restoration in cranberry bogs, which is an interest on the East Coast, where there's a lot of cranberry farms going out of production. So along those lines, we helped develop for a restoration of the Tidmarsh cranberry bog in Plymouth, Mass. Look at how to evaluate some of the different co-benefits, including habitat and denitrification, within the context of a restoration activity, and really be able to look at what the different interests were and how to play, sort of optimize across all of those. And then lastly, we've been exploring the recreational demand and how that is impacted by water quality. So ultimately, we hope this information will help communities understand how to balance social and economic costs and help to start identifying what sort of suite of approaches could be brought together to solve some of these problems. And along the way, really engage stakeholders at the beginning of the process and throughout, and be viewing the transferability of this, so we're not simply focused on Cape Cod, but looking elsewhere. And so this work then became the foundation for our translational science platform. And this is work that has just recently begun. And the goal is to help have solutions-driven research. And translational science is sort of the process by which we deliver solutions-based research. Translational science had a genesis in the public health field, but it's really about how we move from research to solutions. And it is by default or by definition an interdisciplinary activity. The solutions-driven piece emphasizes stakeholder engagement throughout the process. Coordination and communication are key parts. And really, we're trying to apply this translational science approach to achieve better outcomes and evaluate how the process works so that we can inform other groups going forward using these kinds of approaches. Again, we want to inform watershed-based solutions, and we're trying to pilot this solution-driven approach. And ultimately, it's evaluating the effectiveness not just of the solutions that came about, but of the process that got us to the science to deliver those solutions. So part of that's the extent of the effectiveness of the science-based solutions, but also the extent of the stakeholder needs that are met. So the specific case for us is the Three Bays watershed. It's one of those 34 watersheds on Cape Cod that has the TMDL for nitrogen. Their target is to reduce their nitrogen load by a little over 20,000 kilograms per year. Our key stakeholder is the Barnstable Clean Water Coalition. They're a local nonprofit organization, and their director, Z. Crocker, is an enthusiastic partner for this work. And his organization wants to promote a watershed-based solution that uses non-traditional approaches to resolving the nitrogen load problem. They'd like to be a national model, so a place where experiments can be conducted and other parts of the country can learn from those experiments. And they're looking to ensure that it's a cost-effective, science-based solution. We have, in addition to the Barnstable Clean Water Coalition, we have multiple state and local partners engaged on this project. So the first step we conducted was a formal problem formulation workshop, or the first defined translational science approach. There was considerable stakeholder engagement leading up to this, but the problem formulation workshop was to engage stakeholders, local scientists, and the communities to understand the problems, elicit questions and concerns, and really use this to inform the development of our research program. And so we had a one-day workshop, and we had people from across federal agencies, from across EPA, state agencies, towns, and the NGO community. And there's a lot of interest and enthusiasm on Cape Cod for addressing this issue. All the towns are dealing, some in different ways, with their 208 goals. And this, I think, we're able to build off of what's been done and the energy on Cape Cod already, and ideally add something to what folks have been doing going forward. And so in moving from problem formulation to research planning, we distilled what came out of that problem formulation into a couple of key things. First, there's an overall goal of developing a comprehensive approach to reducing nitrogen loading. And that's sort of a long-term goal. And then the objectives we kind of broke down into more time-critical things. So phase one, we heard over and over that pilot a suite of interventions and evaluate their performance at localized scale. So that's actively engaging with stakeholders to identify where and what to do, integrating social science with that intervention evaluation. And that's really the focus of our near-term research, is piloting interventions. Phase two would be implementing an integrated suite of interventions at a scale sufficient to achieve nitrogen goals in a sub-watershed. So this, we heard over, was pick a small system, hit it hard, evaluate it, and understand it. So we're looking at narrowing down the interventions, and then we'll look at scaling that up to a sub-watershed. That's phase two. So the phase one consists of some baseline monitoring so we can understand how the system does change as a result of interventions, and that's groundwater monitoring, and we're working closely with USGS for that. Surface water monitoring, which is being conducted by a number of different partners on the Cape, and evaluation of benthic condition, which will run locally here out of the Atlantic Ecology Division. And then from a piloting interventions perspective, really looking at innovative alternative septic systems as a key part of the solution. And in this case, we want to conduct a neighborhood scale study where we replace an entire neighborhood septic systems with alternative systems, and we evaluate how those systems perform so that we have better understanding of how putting these systems in changes the loading coming from a household, and also look at the groundwater around this neighborhood to look at how that changes, so that ideally we will see a signal in the groundwater and ultimately the surface water, but recognizing that even a large neighborhood of 50 houses is not a big part of a problem that has 6,000 houses in it. So we're trying to work with USGS to narrow down where to do this so that we have the best chance of seeing a signal amidst all of the noise of everything else. But ideally, this will allow the town and the state to better understand how some of these newer septic systems that have potential to get between 5 and 10 milligrams per liter as an effluent, understand how those systems work, and then how that might transpire into the groundwater. We're also looking at permeable reactive barriers, conducting work on shellfish from both a social and ecological side, and looking at some restorations from cranberry bog perspective, as well as some pond restoration. Throughout all this, we want to layer economics of water quality, social acceptance of intervention, and decision support. So we still want to keep that social and ecological connection together. And so to sum up, we've been working on a multifaceted approach to addressing the coastal nutrient problem. We've been supporting the development of sensors to lower costs and improve performance data for innovative septic systems. We've been working on putting together social ecological systems research to address these complex problems. And now we're engaging in a solutions-driven science, nutrients translational science pilot, which is focused on engagement of stakeholders throughout the process, identifying the key research outputs that are most important to stakeholders, assisting our partners to solve their problems, and then ultimately to evaluate how well this translational science process works so that we can better conduct this kind of research going forward, and also that this work be transferable geographically so that what we learn here can be applied in Suffolk County or can be applied in Florida, things like that. So with that, I'll close and open up the line for questions. Thank you very much.
Can you hear me okay?
Yes.
Great. Thanks very much, Tim. So again,